Hello and Namaste. In continuation with the linear algebra topic matrices, we will be going ahead with eigenvalues and eigenvectors with the perspective of applications of them. And we in this particular session will be dealing with the non-repeated, that is distinct eigenvalues. So there are few terms which are you always needs to know. Those terms I would like to take it up or introduce you with the help of matrix. Now this is a simple matrix. I am going to take it just to help to understand, make you understand with the different concepts. What is the first is A minus lambda times I, which is known as characteristic matrix of capital A. This can be calculated using A minus lambda times I, which is this matrix capital A minus lambda times the identity matrix, which is can be written as, or you will get it just a subtraction of these two matrices like this. So only the diagonal elements will change, that is 2 minus lambda, 3 minus lambda, 2 minus lambda and so on. Rest of all the non-diagonal elements of capital A would remain the same. This is known as, this particular matrix is known as characteristic matrix of capital A. If we would go ahead and take the determinant of this matrix, we are going to get something like this polynomial. And if we'll just simplify further, we'll be getting the polynomial in terms of lambda. So if you'll observe here, lambda cube, lambda square, lambda and the constant term. Now this is known as characteristic polynomial of capital A. And if we are taking the determinant, and if we are equating this matrix or this determinant is equals to 0, we will be getting characteristic equation of capital A, and that can be written at like this, and this is known as characteristic equation of capital A. Because we are equating this particular equation with 0, we are taking this plus first term as the plus 1 and then alternate. So automatically this particular thing will happen as plus minus and so on. Now moving ahead with this, suppose we are trying to find out the roots of that particular this characteristic equation. We are going to get the roots as 1, 1, 5. The roots of this determinant of A minus lambda times I is equals to 0 are known as characteristic roots or characteristic values, or latent roots, eigenvalues and proper values. So now what is this? This eigen is a German word. The meaning is proper, and that is the reason one of the name for this particular values are also known as proper values. Now again, suppose we are having lambda 1 is a root of determinant of A minus lambda times I is equals to 0. Then we will have A minus lambda 1 times I is equals to 0, because whenever we are putting the lambda 1, say for example this one we are putting in this particular equation, we are going to get this is the value of this equation is equals to 0. That is what has been written here. Then we find a non-zero. It's very important. I have already defined this in previous session of eigenvalues and vectors, but let me define it again in the particular session here. Non-zero column matrix capital X such that, this is very important property of this, we should not have this capital X is 0. If at all you are getting capital X is equals to 0 at any point of time, that means you should understand that you have made some mistake in between. Capital X cannot be 0. So this system of equations has non-trivial solution, and the vector X is called eigenvector or latent vector, or sometimes it is also known as characteristic vector as well, corresponding to the lambda or to the root of lambda 1. Now what are the important properties? First of all, as we have seen in this particular slide here, in this slide, to reach to this particular step, that is the characteristic equation, and then the eigenvalues, that is lambda is equals to 1, 1, 5, we need to have one step, second step, third step and the fourth step. Rather than that, we can directly go and move with these properties, and these properties are very important with respect to find out the characteristic equation. Now characteristic equation, when we have got A matrix as 2 cross 2 matrix, that time it would be lambda square minus summation of I is moving from 1 to 2, lambda into determinant plus determinant of A is equals to 0. This is directly we are going to check, or we are going to take this as a characteristic equation of the particular matrix of 2 cross 2. Similarly, if we have got the matrix capital A as 3 cross 3 matrix, then the equation becomes here is this, that is lambda cube minus summation of AI into lambda square plus summation of MII into lambda minus determinant of A is equals to 0. Yes, these are the two checkpoints we have to make it down. So we, after this, suppose for example, after this equation, we are getting the values as 115. So we have to check whether those values are correct or not. These are nothing but the checkpoints. The important property number 3 and a 4. Now what is it? The sum of eigenvalues of capital A, that is a trace of A, is equals to sum of diagonal elements of capital A, which is same as summation of AII. That means we have to check whether the summation of the eigenvalues is same as the trace of A or not, and the product of the eigenvalues of capital A has to be equals to determinant of A. Then these are the property which already we have discussed in the previous. Please check the I button. I have given this reference of this particular session. So if lambda 1, lambda 2, lambda n are the eigenvalues of capital A, then the eigenvalues of k into A are k into lambda 1, k into lambda 2 and so on. That means what? If I have got k into A, then k into every eigenvalue will give you the new eigenvalue for this k into A. Similarly, A to the power m has or are lambda 1 to the power n, lambda 2 to the power m. So the power of A, and inverse is nothing but 1 upon lambda 1. So we have already discussed these questions, this particular property before, but I just want you all to have this again here in this session also, because we are going to go with the problem perspective. So what is the problem? First problem I would like to deal, and here in this particular problem I will be dealing with few combined effects. That is, first we are going to find out the values, eigenvalues, eigenvectors, and then we are going to find out, this is very important, which is known as base for eigenspace of eigenspace only for this A actually. And then what we are going to do it, we are going to find out the eigenvalues of this and the vectors as well. Also, we'll be verifying the eigenvectors are orthogonal in pairwise. So in the pair, so we have got this 3 cross 3 matrix as the matrix. Now moving ahead, the characteristic equation is given by this. So this is nothing but lambda cube is lambda cube minus summation of AII into lambda squared plus summation of MII into lambda minus determinant of A is equals to 0. Now how to calculate and how to go about this, the summation of AII, let me just tell you with this. So what is this? This is nothing but the sum of the diagonal elements of a matrix. So please note then, the diagonal elements are 3, 5 and 3. So these are the values. 3 plus 5 plus 3 is equals to 11. That will be giving us the summation of MII, summation of AII value. Then what is this summation of MII means? That means we have to have this as M11 plus M22 plus M33. What is this? This is nothing but a minor of the matrix. Please follow this I button to get back to the minors and all those other concepts of matrices. What do you mean by minor? Minor means we have to take we have to take the minor of this 3 element. So what is this? This is, we have to neglect the first row and a first column. Remaining all these elements, we will be taking this elements ka 5 minus 1 minus 1 3 as the determinant. Similarly, after taking this first, that would be my M11. What would be M22? M22 will be the minor regarding to this 5. That means it is a element placed in second row and a second column. So 3 1 1 3. So that would be determinant of 3 1 1 3 would be coming here, which is M22. Similarly, for this 3, the minor for this 3 is neglecting the third row, third column, will be having 3 minus 1 minus 1 5. And if we are taking the determinant of this 2 cross 2 matrices, that would be 15 minus 1, 9 minus 1, 15 minus 1 respectively. That would be giving me the value of the addition of them is 36. So we got the summation of MII as 36. Then moving ahead with the determinant, now you can have this determinant using the traditional method, using this particular the first row wise, or otherwise please follow the button here, I button. You will be getting the how to calculate determinant of a matrix using the calculator. Matrix mode can be explained here. So this is just, I am not taking the time to make you understand how the determinant will get calculated. Please follow the sessions. Even there are the sessions available how to get the determinant of a matrix in a traditional way is also been given here. So what is this? This is nothing but, hence the characteristic equation is given to us as, so we are just putting these values over here in this case. So it's lambda cube minus 11 lambda square plus 36 lambda minus 36 is equals to 0. That will be giving us the lambdas are 2, 3, 6. That means what? We are getting the eigenvalue for lambda of capital A is equals to lambda, which is 2, 3, 6. What are the eigenvalues of transpose? That is nothing but lambda transpose, but lambda is nothing but the values 2, 3, 6. So the transpose of a real number will not exist. So the transpose of 2 is nothing but 2 itself, because it's not a matrix, it's a real number. So that would be 2, 3, 6 as it is. So you can have one more property here, that is the eigenvalues of A and eigenvalues of A transpose are same. Eigenvalues of A inverse is nothing but lambda inverse. Now inverse means what? It's a reciprocal with respect to the real number. So what is the reciprocal? 1 by 2, 1 by 3, 1 by 6 are the lambdas for A inverse. Then eigenvalues for 4A inverse would be 4 times lambda inverse. So whatever the values we have got it for lambda inverse or 1 by lambda here, we'll be getting that. So it's nothing but 4 into 1 by 2, comma 4 into 1 by 3, comma 4 into 1 by 6. That will gives us 2, 4 by 3, 2 by 3 respectively. Then eigenvalues of A square, that is lambda square, that is 2 square, comma 3 square, comma 6 square, that is 4, 9, 6. Then the values for this matrix, A square minus 2A plus I would be given to us as lambda square minus 2 lambda plus 1, which after putting the values over here, that like lambda is equals to 2 will be getting 1, lambda is equals to 3 will be getting 4, lambda is equals to 6 will be getting 25. Then eigenvalues for this, you can easily check them out here. A cube plus 2I is equals to lambda cube plus 2, which is nothing but, after putting lambda is 2, 10, lambda is equals to 3, we are getting 29, and when lambda is equals to 6, we are getting 2, 1, 8 as the values. Now what about the vectors? Vectors for all of them would remain the same as that of the eigenvectors corresponding to capital A. So we have got the value for lambda is, for A is equals to 2, 3 and 6. So we are getting lambda equals to 2. What is the vector? This is A minus 2 times I into X is equals to 0. I have already defined the vector there. So you can easily check this out here. So determinant, so that is A minus lambda times I into X is equals to 0, where this X is cannot be 0. Please remember this. And this of the lambda, the value of lambda is 2. Therefore this will give you this one. Then just a small subtraction of this matrices will give us this matrix. Now this 2 matrix, 2 value. So if we have got, if you'll see, observe here, the lambdas are here in this case as lambda is equals to 2, 3, 6. So this 2 value is not repeated. If the 2 value is not repeated, we have to go about this type of, to find out the vector, we have to go for the Cramer's rule. Now for that Cramer's rule, we need to have 2 equations, because we have got 1, 2, 3. X, Y, Z, 3 unknowns, and for that reason, to find the value of this particular X, Y, Z, we should have 2 equations for the Cramer's rule. Now again we are selecting the 2 equations distinct, right? For example, if we choose the equation number 1 and the 3, what we will be getting? We will be getting the values of X, Y and Z equals to 0, which is not possible as per the definition of capital X. That's the reason we have to choose 2 distinct equations. So let us choose first and the second one. So we'll be getting 1x minus 1y plus 1z equals to 0. Second equation, minus 1x plus 3y minus 1z equals to 0. Purposely we have written this one because we have to take the determinant of the matrix, the equation. So Cramer's rule will goes as x, then we have the value in the denominator, which is a determinant of, so that what, how can we do that? Whenever we wanted to find out the value below this x, that is the value of x, we will be hiding this x value and remaining minus 1. So if you observe this, minus 1, 1, 3, minus 1, we have taken the determinant, so which is, we have written it here. Similarly, if we are going and trying to get the value for this y, it will be hiding this y equation, then 1, 1, minus 1 and minus 1, which we have written it here. Similarly, we will be going ahead with the z, we will be hiding this z, 1, 1, minus 1, minus 1, 3. 1 minus 1 minus 1 3. So we are going to get, just after solving this particular determinants, we'll be getting this values as x minus 2, minus y 0, z 2. That means what exactly we are getting it? That means we are getting x1 as minus 2 0 2, that is, which is equivalent to, so suppose we are taking it out 2 out from this particular matrix, so we are getting this congruent to 1 0 minus 1. Now going towards the basis, because we have to find out the basis over here. How to go about the basis? Whenever we wanted to find out the basis for any vector, so we have to first take out all the common factors which are there. So now here, if you'll observe, we have got minus 2 0 2, so we have taken it out minus 2 out of this denominator. So after taking this minus 2 out, we will be getting it 1. Anyways, this doesn't matter, y minus y, the value of this minus y doesn't matter here, because we do not have anything here, we have 0, so that will anyways get nullified over here. So this is 1 0 minus 1, which is equals to t. So because we wanted to find out a general value or a basis of this particular thing, so we have to say that is equals to t, and then we have to just say that capital X is equals to, so we are just doing the cross multiplication, so t 0 minus t, taking t out, 1 0 minus 1, that is equals to t times x1. That means what? x1 forms a basis. So what is x1? x1 is this element, that is 1 0 minus 1, forms a basis for the eigenspace corresponding to lambda is equals to 2. This is what is all about the basis of this particular value. So few of the books are giving the direct value, that is 1 0 minus 1, or few of them are giving us the basis of this particular eigenspace. Similarly, this lambda equals to 3, I'll just quickly go ahead, because you can just pause the video, try to get the values for lambda equals to 3. You will get a practice here itself. Nothing new has been there for me to explain here, because whatever I have explained for lambda equals to 2, you have to just replace lambda equals to, in place of lambda equals to 2, you have to replace lambda equals to 3, get the value, get the basis. Basis is also like, if you observe here, this is minus 1 will give you 1 1 1. And we got the basis as 1 1 1 for the lambda equals to 3. Similarly, you can just scroll fast with the lambda equals to 3, and you can see here all the steps whichever we have written. What is the basis will be, you are getting formed here is 1 minus 2 1, 1 minus 2 1. So this can be written as one of the vector, or you can have this as a basis for this particular lambda equals to 6. Yeah. And now the last part is the pairwise orthogonality. What is this? We have got this x1, x2 and x3. So we have taken the basis of all those vectors. Then after taking that, what do you mean by orthogonal? Orthogonal means x1 transpose into x2 is equals to 1 0 minus 1 into 1 1 1. So we are just doing the x1 transpose, because x1 is the column vector or a column matrix. Whenever we are taking a transpose, it becomes a row. Then only the matrix multiplication will happen, and if you observe, this matrix multiplication will gives us the value as 0. Similarly, x2 transpose into x3 will gives us 1 1 1 as a row, and then 1 minus 2 1 as a column matrix. If we multiply them, we will be getting the value as 0. Similarly, the third one also. That means what exactly you are getting it. Hence, the eigenvectors are orthogonal in pairs. All those eigenvectors are orthogonal in the pair. So this is also one of the type of example you might face, or you might have to go with the MCQ type of questions in your competitive examinations. And yes, this is one of my favorite, that is of self-observation slide, wherein I have been given you 1, 2, 3 different matrices along with the lambdas and along with the x1, x2, x3 values. That is actually, in fact, these are not small x1, these are, please consider this as a capital X1, capital X2 and capital X3 values. That means what? These are our eigenvectors corresponding to 1, 2 and 3 respectively. So these are the values I have been given here. Please do solve, go through the session. If you are not getting it, go back and pause it again. Just in case you have any query, write me in the comment box. Thank you. Happy learning.